Hello friends, I welcome you all to my channel. Today I like to introduce another new function, that is Euler's phi function, and how this phi function or Totient function is used in number theory. So what is Euler's phi function? Euler's phi function is also called Euler's Totient function. It is a function that gives us the number of positive integers less or equal to a given number integer n. Those are co-prime to n. It is usually denoted by Greek letter phi, phi. Phi of n is the symbol to represent phi function. Let's see how to calculate phi of n. Phi of n for an input n is the count of numbers in set 1, 2, 3 up to n minus 1. Those are relatively prime to n. Or phi of n count the numbers whose GCD, greatest common divisor, with n is 1 and the number is less than or equal to n. So let us find one by one. First is phi of 1. Phi of 1 is 1 because GCD of 1 and 1 is 1. We don't take count 0. Phi of 2. Phi of 2 is also 1. Why? GCD of 1 and 2, if we take 2, that means 1 and 2. So phi of 1, the GCD of 1 and 2 is 1. So that is one count. And GCD of 2 and 2 is 2. It is not counted. So only 1 is counted here. So phi of 2 is 1. Next is phi of 3. Phi of 3 means we'll take 1, 2, 3. So 1 with 3, they are co-prime. So that is 1. Then 2 and 3 is another one, but 3 and 3, GCD is not 1. So it is not considered. So there are two counts. Here 1, here 1. Or we can take 1, 2 are counted. This is 1, this is 1, 2. Phi of 4. Phi of 4 is 1, 2, 3, 4. So 1 and 4, they are co-prime. So 1 is counted. 2 and 4, 2 is not counted. 3 and 4, again it is counted. So it is 3 and 4 is 1. So it will be phi of 4 is 2. Phi of 5. Phi of 5 is 1, 2, 3, 4, 5. 1 and 5 co-prime. So it is counted. 2 and 5 also counted. 3 and 5 also counted. 4 and 5 also counted. And 5 of 5 is not counted. So 1, 2, 3, 4 are counted. This is 4. Next is phi of 6. 1, 2, 3, 4, 5, 6. So 1, 6, the GCD is 1. Yes. 2, 6, GCD is not 1. So it is not counted. 3 and 6, GCD is not 1, not counted. 4 and 6, not counted. But 5 and 6 are counted. So GCD, phi of 6 is 2. So what will be phi of 7? You can calculate. So these are the phi of some numbers from 1 to 21. You can pause or you can calculate yourself. You can verify whether you are correct or not. But is it possible to find all the phi of n, all the numbers? So there should be some shortcuts or theorems or rules. So let us go one by one. One is theorems related to Euler's phi function. If P is prime, then phi of prime P equals to P minus 1. That means no need of counting. We can simply write down because 1, 2, 3 up to P minus 1 are all relatively prime to P. But 0 is not considered. For example, we had already found that uh, phi of 3, 1, 2, 3. this will be your 1, 3, GCD is 1, 2, 3, GCD is 1. So there was 2. So here this is a prime number. You can directly write 3 minus 1, that is equal to 2. So examples, phi of 5 will be 5 minus 1, 4. Phi of 13 will be 30. This is a prime number, so it will be 13 minus 1 is 12. Phi of 29, this is again a prime number, so we can directly write 29 minus 1 equals to 28. So this is one rule or one theorem. When P is prime, we can phi of prime we can write just minus 1. Now second theorem, if A and B are relatively prime and n equals to product of A and B, then we can write phi of n equal to phi of A multiplies phi of B. For example, if I write phi of 12, phi of 12 is same as your phi of 3 multiplies phi of 4, because 3 and 4 are prime to each other. So let us see some examples. One is phi of 35 can be written as phi 7 into 5, they are prime to each other, co-prime. So it can be 5 into 7, 5 of 5, phi of 7. Multiplication, phi of 5 again can be put into formula, that is, it is a prime number. I can write 5 minus 1, and phi of 7 again prime number. I can write 7 minus 1, 6. So it will be 4 multiplied 6, that will be 24. Let us take another example. Phi of 15, it can be written as 3 multiplication 5. 3 is prime, 5 is also prime, and they are co-prime. So we can put this um, rule. That will be 3 minus 1, 2, 5 minus 1, 4, that is 8. Similarly, phi of 21 can be written as 5 into 3, product of 7. So phi of 3 into 5 of 7, that would be 12. So bigger numbers can be written or arranged in this way. Next is, if P is a prime and n is a positive integer, then phi of P power n equals to P power n minus P power n minus 1. So phi of 2 to the power 5 can be written as 2 to the power 5 minus 2 to the power 4. Phi of 2 to the power P is a prime number. I have taken P is a prime number, 2 prime number. N is any positive number, then it can be written as t to the power 5 minus 2 to the power 4, or 532 equals to your 2 to the power 5 is equal to 32 minus 16, that will be 16. So this is the example we have done. So another is phi of 125. 125 can be written as 5 power 3. So both are co-prime to each other. So I can write 5 power 3 minus 5 to the power 2. That will be 125 minus 25 equal to 100. So next is another theorem. For bigger numbers or complicated numbers, we can use this one. If n is a positive integer with prime factorization of factors p1 power n1, p2 power n2, pk power nk up to, then phi of n can be written as individually this one, this one, this one. So it will be p1 n1 minus p1 n1 minus 1. Individually I am writing for all, p2 power n2 minus p2 power n2 minus 1 up to pk to the power nk minus pk nk minus 1. That means this is same as your phi of p1 n1 multiply phi of p2 n2 phi of P3 and 3, so on up to Pk and K. Again, it can be individually written in this form, 2 to form. Or this is a very useful simplification or derived formula from this. If I take n common, or we can write this thing in this way: phi of n equals to n into 1 minus 1 over p1, 1 minus 1 over p2, 1 minus p over 1, 3, so on. So this is the easier than, simpler than this formula. This is same as derived formula. You can find, or most of the times we use this formula. So let us take some example. For example, 120 can be written as 2 power 3, 8 into 3 into 5. That means here P1 is your 2, P2 is 3, and P3 is 5. Here N1 is 3, N2 is 1, N3 is 1. So when I'll write phi of 120, it will be N is 120 multiplies 1 minus P1, 1 over P1, that means 1 minus P1, here it will be 2, not power 3, 2. Similarly, second one will be 1 minus 1 by 3, this is P2, and 1 minus 1 by 5, that will be your P3. So this is simple. So it will be 120 multiplies 1 and minus half is 1 by 2. 1 minus 1 by 3 is 2 by 3, and this is your 4 by 5. You will simplify. This will be 5 to the 10, 3, 4. Then it will be 4, 4, 16 to 32. So let us find ourselves. Find phi of 92. So I can make the 92 as a factor. 92 is 2 multiplies 2, 4 multiplies 23. So this will be 2 power 2 into 23. So that there are only P1, P2. So phi of 92 equals to 92, that is n, multiplies 1 minus P1, that is 2, multiplies 1 minus P2 equal to 1 over 23. So this equal to 92 multiplies 1 by 2 multiplies 22 over 23. So 23, 4, 2 is 11. So the answer is 44. So phi of 92 equals to 44. So next is find phi of 100. So let's find. We'll write the factorization of 100. It is 2 multiplies 5 multiplies 5. Or this is 2 power 2 and 5 power 2. So there are only two factors, P1, P2. So phi of 100 equals to 100 multiplies 1 minus P1, here 1 by 2, multiplies 1 minus 1 by 5. So please note that it is nothing to do with the powers, only the factor we are writing here, or the prime factors. So this will be 100 multiplies 1 by 2 over 4 by 5. So 2 5s are 10, I'll cancel, so this is 40. So phi of 100 is 40. So this is a very important result for us, because many things will solve in number theory using this fact. As I told, we will use this in number theory. So now, after learning the calculation of phi of a number, then how it is used in number theory. So in a nutshell, we learned that Euler's phi function, phi of n, is the number of integers m belongs to 1 to n with m co-prime to n. Now how it is used in number theory? If a is a co-prime to n, then a power phi of n is congruent to 1 modulo n. This is our applications in number theory. A of any number co-prime to n can be written as a power phi of n is congruent to 1 modulo n. That means a power phi n when divided by n, we get 1 as a remainder. So let us verify. So I have taken 2 phi of 7 is congruent to 1 modulo 7. Let us see. So first I'll calculate phi of 7. We know that 7 is a prime number. So when it is a prime number, phi of p equals to p minus 1. So this will be 7 minus 1, 6. So 2 power 6 is your left side equals to your 64. Now 64 is congruent to 1 modulo 7, right? Because when 64 is divided by 7, we get 1 remainder. So it is correct. So we can apply this concept now. We can take very small. The question is find last two digits of 9 power 201. We have to find the last two digits. That means we have to find the remainder when 9 power 201 is divided by 100. So if we correlate with this phi function, that means we can write the concept here 9, which is a here, because let me write once this theorem, a to the power phi n is congruent to 1 modulo n. Here our n is 100 because we are dividing with 100, and a is 9. 9 and 100 are co-prime. So I can use this here function here. So I can write 9 phi of 100 is congruent to 1 to the 100. That means when 9 power 500 is divided by 100, we get the remainder 1. Now let us find what is the 500. We have already calculated phi of 100. Phi of 100 equals to your 100 multiplies 1 minus half, because 2 is a factor, 1 minus 1 by 5, 5 is a factor, this was 40. Just now we calculated. So 9 power 40 is congruent to 1 modulo 100. So 9 power 201, I'll write this in term of your 9 power 40. So it can be written as 940 multiplies 5, that will be your 200, and another 9 power 1. So this is congruent to, this leaves remainder your 1, because 940 power 5, 9 to the power 40 power 5 to 9 is congruent to 9 multiplies 1 modulo 100. So because 1 power 5 is 100, 1 power 5 is also 1. So the remainder is 0, 9. So when 9 power 2001 is divided by 100, we get 09 is the remainder. So 09 are the last two digits. Let us take another one example. 7 power 2002. Last two digit I have to find. So I'll divide with 100 and find the remainder. So 7 and 100 are co-prime, or GCD is 1. So I can apply this function, phi function here. So phi of 100 equals to 40. We have already calculated. No need of writing again and again. So 7 power 40 is congruent to 1 modulo 100. 2002 will convert in term of 40. So 2002, 2002 can be written as 40 multiplies 50 plus 2. So I need a multiple of 40. So 7 power 40 into 50 into 7 power 2 is congruent to, this is 1 power 50 modulo 100. First one, let me rub this here. So that is same as your 1 modulo 100. Now when I'll write 7,000, 2022, it can be written as 740 into 50 multiply 7 power 2. So it will be 1 into 49 modulo 10. That will be 49 modulo 100. So it is 49. Last two digits are 4 and 9. So next is find last two digits of 2 power 1997. So I can't apply this phi function directly for 2 and 100 because 2 and 100 are not co-prime. So we can go in another way. We can find the 100 can be written as 4 and 25. So once I'll find modulo 4, once I find modulo 25, then we will calculate. Or you can calculate by other method what I have discussed in other videos. Number theory is also has very important use in cryptography. Thank you for watching.